Hi, in this video we're going to do some examples. I call them replacement examples. So let's just look at the first one here. We've got an urn that contains 25 red balls, 15 black balls, and 10 green balls. A ball is randomly selected from the urn, its color recorded, and then it's returned to the urn. The process is repeated 12 times, resulting in 5 reds recorded, 4 blacks recorded, and 3 greens recorded. So we know we've done this 12 times, we got the colors. We want to know the number of distinguishable permutations of the colors recorded. So let me try to explain what I mean by that. So we've got these 12 balls that were recorded here, and we know that there are 5 reds, 4 blacks, and 3 greens. So for example, maybe we had all the reds picked first and then the blacks and then the greens. Probably not. That's not very likely, but maybe we had the greens all picked first and then the blacks and then the reds. That's probably not really likely to happen either. It's probably more likely there was some sort of mixture of the reds and greens and blacks that were picked over, in the different slots and so forth. So probably, some sort of mixture more likely. But any one of these, in fact, that's what we're kind of going to get to, is that for any one of these, there's certain probability that was the selections. And so, again, that's kind of what we're going to get to. We want to determine the number of distinguishable permutations of the colors recorded in this particular example. Now, we've actually already done this. So again, I know that there's 5 reds, 4 blacks, and 3 greens selected. We want to look at the number of different ways that could have been selected, the number of distinguishable arrangements of those colors in those slots. And we did this in a previous video back in the last video. We did this in a little bit different context. We had books on a bookshelf. We had 5 identical looking math books, and then 4 identical looking history books, and 3 identical looking chemistry books. And we talked about the number of ways of arranging those books on the bookshelf, the number of distinguishable arrangements or distinguishable permutations of those books on a bookshelf, and we found that it was 12 factorial divided by the product of 5 factorial, 4 factorial, and 3 factorial. This is mathematically the same question, it's just a little bit different context. So the answer to our question here is the number of distinguishable permutations of the recorded colors is, again, this expression which calculates to 27,720. Okay, now on an exam you're probably not going to be asked this question, but a question very similar to it. So let's look at the next example. Same setup, but now the last sentence has changed. Let's determine the probability that exactly 5 reds, 4 blacks, and 3 greens were recorded. And notice that because we're selecting a ball from the urn and then putting it back into the urn, at any time there's going to be 25 red balls in the urn and 50 total balls. And so the probability of selecting a red ball is going to be 25 out of 50. The probability, likewise, similar argument, probability of selecting a black ball is 15 out of 50, and probability of selecting a green ball. Every time we reach in there, we're selecting a ball, but then we're putting it back. So each time we make a selection, the probability of a green ball being selected is 10 out of 50. So I'm going to replace these with the decimal values. 0.5 for the probability of a red ball, and 0.3 probability of picking a black ball, and 0.2 for the probability of selecting a green ball. Okay, so now I've got 5 reds, 4 blacks, and 3 greens listed out. Now I don't know which order they're in. That's kind of the first part of the first example, to find the different ways of ordering. But I do know that 5 times for 5 of those selections there's going to be a red ball, and the probability of selecting that ball was a 0.5. So if I look at the probabilities of selecting the ball in each slot, 5 times I'm going to have a probability of 0.5, 4 times I'm going to have a probability of 0.3, and 3 times I'm going to have a probability of 0.2. So for each arrangement, then the probability of getting that particular arrangement is 0.5 to the 5th, 0.4 to the 4th, and 0.2 cubed. And then from the first example, we need the first example to finish the problem. From the first example, we know that there were 27,720 distinguishable arrangements or distinguishable permutations there. And so the probability, my answer here, the probability of selecting, of having 5 reds, 4 blacks, and 3 greens in this situation will be the 27,720 times that p-value there, which ends up being about a 5.6% probability. Okay, so now let's look at another example. Let's switch it up a little bit now. Now this time I've got 25 reds, same setup. I've got 25 red balls, 15 black balls, and 10 green balls in an urn. This time the 12 balls are randomly and simultaneously selected from the urn. Now, let's compare that back to the first two example problems, which is the ball is selected from the urn, its color recorded, and then it's returned to the urn, and the process is repeated 12 times. Now, 12 balls are randomly and simultaneously selected from the urn, and mathematically, if you're going to take all 12 balls, you're going to reach in and just pull 12 balls out, it's mathematically the same as reaching in, selecting a ball, and then not replacing that ball and selecting another ball. So mathematically, it's the same as 12 balls are randomly selected from the urn without replacement now. Okay, and so that's going to be our setup now. We want to determine the number of ways in which the selection of the 12 balls would result in 5 of them being red, 4 being black, and 3 being green. It's a little bit different question than the example 1 question, and I'm going to come back to that later in the video. But for right now, let's answer this question. What's the number of ways we're counting here? What's the number of ways for this event to occur? The event being that 5 reds, 4 blacks, and 3 greens were selected from the 12 balls. And so, being a counting thing, let's kind of let's use let's break it down into tasks. That's our job. And our first task will be, well, what is the number of ways that we could have selected the 5 red balls? And again, we're counting, so we go back to our learning video where we had this flow chart. And the first question in the flow chart, well, are repetitions allowed? And of course, now since you're not returning the ball into the urn, it's kept out of the urn. You can't select the same ball twice. So repetitions are not going to be allowed. And then the next question, well, does order matter? And my claim here is that order does not matter. And let's go through that thought process. What that means, does order matter? Well, let's say that you've selected the 5 red balls. You've got those 5 red balls that were selected, and you select those. And now if you selected the same 5 red balls, but kind of in a different order, I mean, you're just kind of, you got the same set of 5 red balls. And so the order didn't matter in which you selected them. Again, if I'm thinking of reaching in there, grabbing a ball, and not replacing it, and then reaching in there, grabbing another ball and not replacing it. And let's say that I've grabbed 5 red balls, and if I grab the same 5 balls in a different order, I've got the same set of 5 balls there. I've selected the same 5 red balls. So the order does not matter. And then our flow chart would say, well, you want to use a combination calculation then. So the number of ways to complete task 1 would be, out of the 25 red balls, we're selecting 5, so it's 25C5 or 25 choose 5. Likewise, I think you see what's going on now. Let's look at task 2. Let's say task 2 is selecting the 4 black balls. Once again, repetitions, same reasoning, repetitions not allowed, order doesn't matter. So the number of ways of completing task 2 would be a 15 choose 4. And then finally, if define task 3 to be the number of ways of selecting 3 green balls, then the number of ways of completing task 3 would be 10 choose 3. And then the fundamental counting principle would say, well, the number of ways of completing the job, the number of ways of selecting, in which the selection of the 12 balls would result in the 5 reds, the 4 blacks, and the 3 greens. Well, you multiply together the number of ways of completing each of the tasks. And this ends up being quite a big number. It's 8.7 billion number, 8.7 billion number there. Okay, once again, this is probably not going to be the type of question that you're asked on an actuarial exam. We're going to tweak it just a little bit. Same setup, but now the last sentence is going to be, let's determine the probability that exactly 5 of the selected balls are red, 4 are black, and 3 are green. Now we've kind of done the hard part with we've kind of done the hard part in the last example. If I define E to be this event that I have 5 reds, 4 blacks, and 3 greens of the 12 selected, then just basic definition of probabilities. The probability of an event is the number of outcomes, the number of ways that the event can occur divided by the number of outcomes in the sample or the survey. And so we've actually done the harder problem here. The harder part is the numerator, find the number of ways that the event can occur. We did that in example 3. In the denominator, what's the number of ways, number of outcomes in the sample? Well, the experiment here is you're selecting 12 balls out of 50. And for the same reasons as before, when we're counting the number of ways of selecting 12 balls from the 50 balls, the order, the repetitions are not going to be allowed. I'm not replacing the balls when I pick them out, so the order does not matter. I'm sorry, repetitions are not going to be allowed. And again, same reasoning, the order is not going to matter. So the number of outcomes in the survey is 50, choose 12. And so the probability of this event is this ratio, which ends up being a little over 7%. Okay, so I used a little bit different technique in example 4 than I did in example 2. Both were calculating probabilities. I used a little bit different technique, and so let's kind of look at those two situations. Both of them relied on being able to do a counting argument first. So let's look at example 1 and example 3 first. I've kind of highlighted or put in bold here the differences here. In example 1, a ball is randomly selected from the urn, its color recorded, and then it's returned to the urn, and the process is repeated 12 times. This is a very different question than what's in example 3, which is just that the 12 balls are randomly selected from the urn without replacement. Number 1, I wanted to calculate, given that I had 5 reds, 4 blacks, and 3 greens, and number 1, I wanted to calculate the number of distinguishable arrangements or distinguishable permutations of recording those colors. Very different question than in example 3, which was just to determine the number of ways that of the 12 selected, I had 5 reds and 4 blacks and 3 greens. And so this is just a different technique on counting, because the problems are, we're tasked to do different things. In example 1, we found that there was, this is just an example of determining the number of distinguishable permutations, whereas example 3, we used a fundamental counting principle argument. Okay, and both of these were used for examples 2 and 4, which is probably what you're more likely to see, which is probabilities here. Example 2 is to determine the probability where we had replacement of the balls. Example 4 was to determine a similar probability where there was not replacement of the balls that were selected in the urns. And again, we had to use the counting arguments from examples 1 and 3 in order to calculate the values, the actual probabilities in examples 2 and 4. And so you can see from examples 2 and 4, these were our answers from example 2 and 4, and the 27,720 came from having to do a count in example 1, and then the 8.7 billion number that I have highlighted in red at the bottom is number of ways of completing, or the number of ways of the event that the event could occur, which was in example 3, what we did in example 3. Okay, so it looks like I used different techniques, and if I was asked to do each of these problems, I've just shown you exactly what I would have done to do each of these problems. Now, if you look at example 2, how we approached example 2, we looked at, okay, well, for a certain arrangement, what's the probability that was the arrangement, or what's the probability that arrangement occurred? And then we multiply that by the number of that 27,720, which was the number of distinguishable arrangements or distinguishable permutations of that particular, of the colors recorded, I should say. Okay, and then example 4, I used a different technique when I had a problem that was without replacement. And so, again, that's what I would do, but I want to show you an alternative solution to example 4 where we use the same process as what was in example 2. So let's look at that real quick. So in this case, I'm going to kind of list out the slots here, and I know that I've got 12 balls that I'm selecting from the urn, this time without replacement, and I want to know what's the probability that exactly 5 were red, 4 were black, and 3 were green. Okay, so now I don't know what color the first ball is, but the probability of selecting that ball is something out of 50. And likewise, I don't know what color the second ball is, but the probability of selecting that second ball, since I didn't put that first ball back in, the probability of selecting that second ball is something out of 49, and so forth. And so then for each arrangement, I don't necessarily know what the colors are, but for each arrangement, I'm going to have a probability. I'm going to multiply all those probabilities together. That's what the fundamental counting principle would say. I'm going to multiply all those probabilities together, and in the denominator, I'm going to have 50 times a 49 times a 48, and so forth, where that product has 12 factors. And in the numerator, I don't know what the first numerator is. I don't know what the second numerator is, but I know that since I had 5 red balls and 4 black balls and 3 green balls, that 5 of the numerators are going to be, let's see, 25, 24, 23, 22, and 21. And then 4 of the, I hope you see where I got that, 25 out of 50, I got 5 red balls. There were 5 red balls in there. So I had, in the numerator of one of those is a 25, and the numerator of the next one where there's a red is a 24, and so forth. And I can go through the same argument for the black and the green balls, and then I see that for each arrangement, the probability of that particular arrangement then is this is this ratio. In the numerator, 25 times 24 times 23 times 22 times 21. And then for the blacks, it's 15 times 14 times 13 times 12. And then for the greens, it's 10 times 9 times 8. That's for each arrangement. And then how many different arrangements do I have of the colors? How many different ways can I arrange those, distinguishable ways can I arrange those colors? Well, that's the example 1 question, that there was 27,720 distinguishable arrangements of those colors. And so again, I get back to then the probability that there were 5 reds, 4 blacks, and 3 greens selected would be this 27,720 times that p-value, and I get the exact same number that I got before when I did example 4 using the alternate approach of just looking at the definition of a probability, the number of ways for the event to occur divided by the number of ways that the sample space can be, number of outcomes in the sample space. Okay, I want to show you quickly why why we got the same 2 answers. And so let me make a little bit more room here. The first way that I did example 4, I got this ratio in the numerator of 25 choose 5 times a 15 choose 4 times a 10 choose 3, and then the denominator of 50 choose 12. And then the second way, I didn't put this 27,720 there, but that's actually this first factor. That's the 12 factorial divided by the 5 factorial, 4 factorial, 3 factorial. That's how you calculate the number of distinguishable permutations that we did in example 1. So what I want to point out here is that, let me highlight in red, let's group some of these factors together. If we group the 25 times 24 times 23 times 22 times 21 in the numerator with the 5 factorial in the denominator, that will exactly give you a 25 choose 5. So I'm going to replace that with a 25 choose 5. I invite you to do the arithmetic yourself. I'm going to move to the green ones now. So if you look at the 10 times 9 times 8, group that with the 3 factorial, that will exactly give you the 10 choose 3 factor that's in the numerator of the expression above. And let me highlight them, and let me bold the ones in black here, the 15 times 14 times 13 times 12, divide by 4 factorial, that gives you exactly the 15 choose 4. And then I'll again leave it to you to show that the rest here, the 12 factorial that I've highlighted in blue here, if I group that with the denominator, it becomes the 50 choose 12. The 50 choose 12, when you write that out, it'll be a fraction. So you have a fraction in the denominator, and the complex fraction that you get, when you simplify that complex fraction, you'll get exactly what's shown here. And so so that's an illustration of why you get exactly the same answer, whether you choose to do example 4 like we did, like I did originally. That's how I would do it originally, or if you chose to do it using this expression right here that is kind of more similar to what you would get in if you use the approach from example 2. Okay, so there was a lot to this video. I think it's a good video and good stuff in the video, and I hope you think so too, and I will see you in the next one. Have a good day.